Every takeoff hides an invisible rivalry. Two flap designs, Fowler and Krüger, split the world's biggest airliners, and no passenger knows the engineering battle shaping how they fly. One design can add 25% more wing area and nearly double the lift, but it weighs hundreds of pounds more. The other achieves higher efficiency with a clever hinge, but it faces unique dangers. Why are Boeing and Airbus trapped by these billion-dollar choices, and what do they not want you to see beneath the wings? The answer begins with a mechanical divergence that still defines modern flight. In 1924, Harlan Fowler patented a new kind of wing extension that would change the way aircraft handled low-speed flight. The concept was simple in theory, but complex in execution. Fowler designed a flap that did not just hinge downward, but first slid rearward along heavy-duty tracks built into the wing trailing edge. This two-stage movement, first back then down, lets the flap increase both the camber and the total area of the wing. When fully deployed, a Fowler flap can boost the wing surface area by as much as 25%, transforming a sleek jetliner into a high-lift machine ready for slow-speed takeoff or landing. The heart of the system lies in its rails and tracks, engineered to bear enormous forces as the flap glides smoothly backward before rotating into position. This motion creates a slot between the main wing and the extended flap, channeling high-pressure air beneath the wing up and over the top surface. The result is a dramatic increase in lift, especially at lower speeds, without a steep penalty in drag during partial deployment. It is a design that rewards precise engineering and robust materials, qualities that Boeing embraced as it standardized Fowler flaps across its entire jet lineup. From the 737 to the flagship 787, every major Boeing airliner relies on this sliding, rotating mechanism to deliver safe, efficient performance at the edge of the flight envelope. The complexity of the Fowler system is not just in its movement, but in the infrastructure it demands. The tracks, bearings, and actuators add weight and require exacting tolerances. Yet for Boeing, the benefits, greater lift, variable geometry, and reliable handling, have made the Fowler flap a permanent fixture beneath the trailing edge, shaping the company's engineering identity for nearly a century. Werner Kruger's breakthrough in 1943 offered a completely different solution to the challenge of high-lift flight. Instead of manipulating the trailing edge, Krüger focused on the wing's leading edge, designing a robust panel that hinges forward and downward from beneath the wing. When deployed, the Krüger flap swings out into the airstream, increasing the leading edge radius and thickening the wing's profile. This adjustment delays the point where airflow separates from the wing, allowing the aircraft to maintain lift at lower speeds and higher angles of attack. The mechanics are deceptively simple. A single hinge line runs along the front spar. As the flap rotates forward, it forms a smooth, continuous curve with the wing's upper surface. Unlike slats or Fowler flaps, there is no slot or open gap, just a seamless extension that preserves aerodynamic cleanliness. This design minimizes turbulent flow and helps control the boundary layer, reducing the risk of abrupt stall. The absence of complex tracks or actuators keeps the system lighter and less prone to mechanical wear. Airbus has standardized Krüger flaps across its entire jet family, from the narrow-body A320 to the double-deck A380. This consistency reflects a belief in the efficiency of leading-edge boundary layer control. The Krüger approach does not increase wing area like Fowler's, but it achieves remarkable lift gains with fewer moving parts. For Airbus, this forward hinging panel represents a quiet revolution, an elegant low-drag answer to the demands of modern commercial flight. Wind tunnel testing draws a sharp line between the two flap philosophies. With Fowler flaps, the numbers are clear. At 30 degrees of deflection, the system delivers a maximum lift coefficient of 1.9. That figure represents a dramatic boost over a clean wing. But the method comes with a price. The Fowler mechanism, with its robust tracks and actuators, adds about 400 pounds to each wing. This extra mass is not just theoretical. It is built into every Boeing jet that relies on the Fowler design, affecting payload and fuel calculations from the start. Krüger flaps, in contrast, achieve a higher lift coefficient, 2.1, while keeping the mechanism simpler and lighter. The absence of sliding tracks or multiple slot elements means less structural weight, a difference that accumulates across an entire fleet. The Krueger approach also generates less drag at comparable deployment angles, a result confirmed in controlled aerodynamic studies. For Airbus, this translates into a quantifiable efficiency edge during low-speed flight phases. The weight penalty of Fowler flaps is not just a footnote in engineering reports, it shapes every aspect of aircraft performance. A heavier wing means higher fuel consumption, altered takeoff speeds, and stricter limits on payload. The aerodynamic gains are real, but so are the trade-offs. Meanwhile, the Krueger system's lighter structure and higher lift coefficient set a different baseline for efficiency, one that will echo through every cost, range, and runway calculation that follows. Inspection. Schedules drive the economics of flap design as much as aerodynamics. In the field, Fowler flap tracks demand close attention every 500 flight cycles. Each inspection means removing fairings, checking for wear, and testing actuator response. Airline maintenance logs reveal a recurring pattern. Bearing failures in the Fowler system are responsible for about 15% of dispatch delays on Boeing fleets. A single seized bearing can ground a jet, ripple through a schedule, and trigger costly part replacements. The complexity of the track mechanism, rails, rollers, and actuators translates into higher man-hours and more frequent unscheduled repairs. Replacement of a Fowler track assembly can cost an airline up to $180,000 per event. That figure includes both hardware and labor. Krueger flaps, with their simpler hinge design, avoid much of this burden. Their main vulnerability is long-term fatigue at the hinge line. After 20,000 cycles, stress fractures can appear, requiring hinge replacement at a cost closer to $95,000. Maintenance planners favor the predictability of this failure mode, as it aligns with scheduled heavy checks and rarely causes abrupt service interruptions. On the Airbus side, annual maintenance hours for Krueger systems run about 30% lower than for Fowler-equipped jets. Operational data highlights how these differences appear on the runway. A Boeing 737 typically needs 1,430 meters to land, while an Airbus A320 at the same weight requires just 1,380 meters. Takeoff rotation speeds show an 8-knot advantage for the Airbus. The weight penalty of Fowler hardware also adds up in fuel burn. Boeing jets consume 1.2% more fuel per flight, a small figure that becomes a major cost across an airline's annual schedule. For maintenance managers and flight crews, these numbers are not just statistics. They define reliability, profitability, and the margin for error on every flight. Switching flap systems isn't just a technical headache, it is an economic impossibility. Boeing's commitment to the Fowler flap runs deeper than engineering preference. Over $14 billion has been sunk into specialized tooling, automated assembly lines, and supplier contracts, all designed around the sliding track mechanism. Every jig, robot, and fixture on the production floor is tailored to this architecture. Changing course would mean scrapping decades of investment, halting deliveries, and rewriting thousands of engineering drawings. The barrier does not stop at hardware. 50 years of pilot training, flight manuals, and simulator programs are built around the Fowler system's behavior. A senior captain with 20,000 hours on Boeing jets said, "You don't just swap out the flaps, you rewrite the way the airplane talks to you on approach." That institutional knowledge is woven into checklists, emergency procedures, and regulatory approvals worldwide. Airbus faces its own kind of inertia. The Krueger flap's simplicity brings efficiency, but also unique vulnerabilities. Ice can build up on the exposed leading edge, and the system's limited deployment options restrict flexibility in abnormal situations. Admitting these drawbacks would mean questioning the foundation of their fleet and opening the door to costly retrofits. Legal barriers reinforce the technical ones. Boeing holds 47 active patents on Fowler improvements, and Airbus controls 31 patents for Krueger designs. A cross-licensing agreement signed in 2007 was supposed to break the deadlock, but neither company has ever exercised those rights. Each is trapped by its own legacy, watching as new adaptive trailing edge technologies like NASA's morphing wing promise to outperform both systems. Yet with over $200 billion invested industry-wide in existing infrastructure, the risk of abandoning the old ways outweighs the lure of innovation. A survey of 10,000 pilots revealed that 68% prefer the tactile feedback of Fowler flaps, citing better low-speed handling and more predictable stall warning. Still, the engineering teams on both sides know the real contest is not just about lift or drag, but about who can afford to walk away from their past. Today, legacy engineering choices still dictate every major airliner's wing, locking billions in technology from another era. As commercial aviation faces new pressures for efficiency and sustainability, the real challenge is not lift or drag, it is whether the industry can finally let go of its own inertia. What would you change?